Have you ever stopped to think about how your phone just knows where a face is in a photo, or how a self-driving car can spot a person on the street? It's something we do without thinking, but how on earth do you teach a machine to see? Well, today we're going to pull back the curtain and take a look at the magic behind it all, how an algorithm learns to tell the difference between a boat, a bird, or anything else really, all from a bunch of pixels. Let's dive in. So, take a look at this. You and I, we can tell what's a boat and what's a bird in what, a fraction of a second? It's automatic. But for a computer, this is a seriously difficult puzzle. How does it even begin to make sense of all this visual noise? That's the big question we're going to tackle right now. Okay, so the first thing you've got to understand is that computers don't see pictures like we do. Not at all. Where we see a boat sailing on the water, a computer just sees a giant grid of numbers, a massive spreadsheet, basically. Each number is just the color and brightness for one tiny little dot, one pixel. The whole beautiful image, to the machine, it's just data. So, how do you get from that grid of numbers to boat? You use a special kind of brain, a tool called a convolutional neural network, or CNN for short. And what you're looking at here is its basic blueprint. Think of it like a digital assembly line for images. The picture goes in one end, it passes through these things called convolutional and pooling layers, which find all the important patterns, and then it gets to the end, to the fully connected layer, which makes the final decision. We're going to walk through each of these steps one by one. So first up is the most important step in the whole process, convolution. The network's first job isn't to see the whole boat. No, it's got to start much smaller. It's trying to find the most basic building blocks of the image, things like simple lines, edges, corners, and curves. So how does it actually find those little features? It uses this really clever process called, you guessed it, convolution. The network uses a tiny little detector, which we call a filter or a kernel. You can think of it as a tiny grid of numbers that's been designed to look for one very specific pattern, like a vertical edge or a curve that goes from left to right. By sliding this little filter across the entire image, the network builds a brand new map, a feature map, that basically lights up wherever it found that one specific thing it was looking for. Let's really break that down with the sliding window idea. Imagine you have a tiny magnifying glass, that's our filter, and you slide it across the image, pixel by pixel, never missing a spot. Every time it stops, it does a quick bit of math. It multiplies its own numbers by the pixel numbers it's looking at, and then it adds all those results up into one single number. That new number becomes a single pixel in our feature map, and it does this over and over and over again for the whole image. And right here, this is the engine that powers that whole sliding window operation. Now, I know formulas can look a little intense, but this is just a fancy way of writing down exactly what we just talked about. The C on the left is our output, that one new pixel in the feature map. It's calculated by taking the input pixels from the image, that's the X, multiplying them by the filter's values, our W, and then adding a little tweak called a bias, the B. That's it. That simple little operation, repeated thousands of times, is how the network first starts to see. Okay, so at this point, the network has found a ton of features, all sorts of edges, curves, and textures, but are they all useful? Of course not. So the next step is to add a kind of decision maker into the mix, something that can decide which features actually matter and which ones we can ignore. And this is where something called activation functions come into play. Their big job is to introduce what's called nonlinearity. And here's what that means in plain English. Without an activation function, the network is only capable of learning things in straight lines. But the real world is messy. It's full of curves and complex shapes. To recognize the gentle curve of a sail or the weird outline of a bird, the network needs to be able to learn those complex, nonlinear patterns. Activation functions are what give it that superpower. And, you might be surprised at how ridiculously simple the most popular activation function is. It's called ReLU, which stands for Rectified Linear Unit, and it basically works like an on-off switch. So after a neuron does its calculation, the result gets sent to ReLU. If the number is positive, the switch is on, the value goes through. But if the number is negative, the switch is off, it just gets turned into a zero. That's it. It's an incredibly simple way to force the network to focus only on the features that are sending a strong, positive signal. All right, so now our network has created dozens of these refined feature maps, highlighting all the important little edges and curves. But this is still a massive amount of data. To keep things from getting out of control and to start focusing on the bigger picture, the network needs to summarize what it's found. It needs to get more efficient. And that next step is called pooling. You can think of it like shrinking the feature map way down while still keeping the most important bits of information. This does a few really critical things for us. For one, it makes the network way faster. It also makes it more robust, meaning if the boat is in a slightly different part of the image, the network can still recognize it. And maybe most importantly, it helps prevent something called overfitting. Overfitting is basically when the model memorizes the training pictures instead of actually learning the concept. Pooling helps it generalize so it can recognize boats it's never seen before. Now, there are a couple of popular ways to do this pooling. Over on the left, you have max pooling. It looks at a small window of pixels and just keeps the single biggest, most intense value. This is awesome for capturing the sharpest, most prominent features. Then on the right, you've got average pooling. It looks at that same window but takes the average of all the values inside. This gives you a much smoother, more generalized summary of that little area. Which one you use just depends on what you're trying to do.
Okay, we are on the home stretch now. Let's see how all this hard work comes together. We've detected features, we've decided which ones are important, and we've summarized them to be more efficient. Now it's finally time to put all those clues together and make the final call.
And that final decision happens in what's called the fully connected layer. The name pretty much says it all. Every single neuron in this layer is connected to every single neuron from the layer that came before it. Its job is to take all that high-level, processed feature information, all the evidence that's been gathered, and weigh it all to make a final prediction. This is the part that acts like a board of directors, looking at all the reports and casting the final vote. And voila, here is the result of that final call. For the image we've been using, the fully connected layer has crunched the numbers and calculated the probabilities, and it's 94% confident that the image is a boat, a tiny chance it's a cat, even smaller chance it's a bird. This right here is the payoff moment, where all those layers of abstraction, from simple edges to complex patterns, finally come together to give us one simple, human-readable answer. You know, this quote from Ujjwal Karn's blog really just nails the whole thing perfectly. The first parts of the network, the convolution and the pooling, they're the feature extractors. Their only job is to boil the image down to its most important parts. And then that fully connected layer comes in at the end to act as the classifier, using all those features to make the final judgment call. It's a beautiful two-part system.
So there you have it. From a simple grid of numbers to a confident classification of boat, that is the incredible journey a computer takes to learn how to see. It's an unbelievably powerful process that is changing, well, pretty much everything. And it leaves us with one last, pretty exciting question to think about. If we can teach a machine to see, what on earth will we teach it to understand next?